All right, good morning. There's a small technical difficulty. I wanted to change the slides in the last second, but it didn't work. So welcome to the, to the 6th lecture in our course. Before we start, as I promised, I would like to show you the results from the survey that we had. About 42 people out of 120 registered students voted, so that's less than, it's about 30%. It could have been somehow better, but I'll take these results as representative nevertheless. All right, so quickly. All in all, the feedback was somehow positive as far as my personality goes. I was trying to identify areas for improvement for the course and also for myself, and I think I found some. I'm going to show you those. But before that, the quick aggregated results. So the questions, most of you attended all the exercises. I appreciate that there were honest people who simply didn't care, and they were honest enough to say it. So most of you seem to be satisfied with the exercises so far. This could get a little bit better. I hope with the Vensim models it will get better. Well, I should have zoomed in so much, actually. Yeah. Well. So, I'm happy to see that somehow I managed to explain at least the most important things, and yeah, that's a good thing. Now, this is a question which I believe could be improved, and I was thinking about how to improve it. It's about how the exercises are coordinated with the lecture, and there is a good 10%, or let's say aggregate 25% of people who are somehow on the border between thinking that they fit and thinking that they don't fit. I will come back to this question when we go through the manual feedback. So this is my favorite question. Well, yeah, after the survey, it became my favorite question. Yeah, so, I mean, thanks for that. I certainly do try, but this makes things actually more difficult for me. Because, you know, with great power comes great responsibility. So it's very easy from here to go deep into the ground. But I'll try for this not to happen, of course. The airport cases, the majority thinks they were interesting. Still, there are people, 8% in total, who don't agree at all. And I was looking for some kind of manual comments to see why. I think I know why. So we'll get back to this as well. This is all right. The topics are interesting. I believe this could be improved. I did not write all the text in the self-studies, but now that I read it again and again, I believe there is something to be improved purely in the presentation style, so that's going to happen. This is also kind of a good feedback. But then again, these were just 4 lectures, so I'd be interested to see how this thing develops, this question in particular. I see value in attending the lecture. This is good. The self-studies should not be too difficult, should not take you too much time. And this is the most concerning question, actually, for me. This question was not present in previous years. I came up with it this time. And it seems that, I mean, I see this as kind of my fault, because there is a good percentage of people who don't see what the purpose of this course is and how each lecture builds on top of the previous one. I see this as basically failure to communicate this effectively from my side. Yeah, I mean, what can I say? My goal here is every time to reiterate the overall structure of the course and where we are currently. And I thought that would be enough to give you an impression of where we're going, where we're heading, but it seems not to be enough. So I'll be thinking how to maybe change the introduction of the lecture so that you get more kind of memories from previous lectures. The pace of the course seems to be all right. Okay, then I will not show you this. I mean, I will show you this, but kind of a stripped down version of it. So these were the multiple choice questions. Now we go back to to the lecture and to the manual feedback questions. I'm using a Acrobat Reader because something is wrong with my graphics driver, and other PDF readers don't work for some reason. So let's discuss the manual input questions and the feedback that you gave me there. I tried to find out the main themes or the main kind of concerns that you have. The first one is this one. No formal way to solve problems is taught. Actually, it's a quotation. You see, this was not the purpose of the course, to teach formal ways to solve problems. The purpose of the course is to introduce the problem-solving part before we go to the systems dynamics part. Systems dynamics is basically about trying to find out how systems work and why they don't work. But you don't start from here, from that part. You start before the system is being built, by identifying the problem, trying to come up with the better solution, and then designing your system according to the better solution that you hopefully you have found. So the purpose of the first part of the lecture was just to give you a flavor that this thing exists, that you need to do problem solving. There was a general guideline in terms of the problem solving cycle, how you go about this situation analysis, selection of solutions, so on and so forth. But this course is not about formal ways for problem solving. In particular, given the fact that the problems we tackle, they don't have a formal way of solving them. It's all about you as problem solvers, individual problem solvers. You have to go through the discussions. You have to go through all these reiterations of the problem solving cycle, situation analysis, try to find out what your client wants. So it's actually difficult to teach a formal way to solve this kind of problems. How do you teach a formal way to solve the self-study with the airport? I cannot think of anything like this. So first of all, this course was about giving you, the first part of the lecture was about giving you an idea that problem solving needs to be done before you start modeling with Vensim or writing differential equations and stuff like this. So if you expected this, then probably I didn't communicate this well enough in the beginning. And second of all, there is no formal way for our problems. There are general guidelines or frameworks, but not the formal way. Second, some of you wanted more real-life examples of the problem-solving cycle. So more case studies like the airport. This is a good point. I'm thinking maybe we can drop one of the self-studies, in particular the fourth one with the SWOT, or maybe modify it in a way that there is a real business case behind it, where you can apply the SWOT and the problem-solving cycle. But that would not affect you, actually. That would affect the next batch of students. But it's a good point because, I mean, we had two self-studies for the problem-solving cycle. Either we can make them more precise, so reduce the scope of the problem, or we can make 3 self-studies for the problem-solving cycle. I have to discuss this with Professor Schweitzer and get his opinion, but it's certainly a point that I will keep in mind. Next one, there was a lot of suggestions, complaints about the self-study presentations. In particular, you wanted, or some of you, those who gave the feedbacks, wanted less presentations and more discussions. So if we have 2 or 3 groups presenting for 45 minutes, naturally this cuts down on the time we have for discussion. And there were suggestions, actually. I appreciate this. Not just criticism, but also suggestions how we can do this. Maybe just part of the problem is the problems are split among the groups. And I was thinking about this, actually, for a couple of days. And this is what I think now. You see, for the first part of the lecture with the problem-solving cycle and this kind of discussion-oriented self-studies, I think we had discussions. I mean, we certainly discussed the airport example. We tried to discuss the SWOT case. But importantly now, when we go to the Vensim models, and I will address this in the lecture as well, modeling is a lot about intuition. It's a lot about developing, doing it yourself, basically, learning by doing. There is no way that you can, or modeling can be taught in a way that you get a feeling how to identify the proper feedback loops, how to identify the critical parameters. There is no formal way for this. There is no theory for this. There is intuition. It's like learning to program some computer language, learning to program without ever doing it, just by somebody discussing null pointer exceptions or stuff like that. So the self-studies until the end of the lecture are going, well, let's say, what you can get from these self-studies depends a lot on you doing stuff, not so much on discussing. Because you can have 40-minute discussion on this feedback loop and this critical parameter, and you will think you've understood it. But when you get to do it yourself, you won't have this kind of feeling what to do, because you've never done it. So the important thing for the coming self-studies is that you do stuff. And even though we may not have enough time to discuss every single feedback loop, every single parameter that you can vary, if you've done it yourself, that's good enough. Having said that, I'm pretty sure we're going to have time to address the most important things in all the models that we're going to see. What are the most critical parameters? What is the most important thing that you should get from this model? So this is my goal for the coming self-studies. But discussions, so bottom line is discussions will not help you for learning how to model. It's really learning by doing. And the purpose of the self-studies is to give you an opportunity to learn this, to develop this intuition. All we ask for is one presentation and one active discussion. We think that this is the minimum activity required, at least to get you interested and give you some kind of practical sense. So I don't see how more discussions will be useful for the coming self-studies. Another thing, groups were concerned that the value of their presentation is greatly diminished if they're not first, meaning that the other group would have probably mentioned everything that they wanted to mention. So they see this as a waste of their effort. It's wrong, because even if your presentation is identical, well, not identical, of course, but has the same messages as the previous groups, the important thing is that you did it and you learned by doing it. And this is the point of the exercise. The point of the exercise is not to polish up your presentation skills, but to learn how to do it. So this will not only help you, you've done it, but it will also help the audience, because if we reiterate a point, it's just more likely that the audience gets it. All right, so don't be concerned if your presentations have huge overlaps. And so far, there haven't been huge overlaps, I have to say. But even if that's the case, that's not the important thing. You learn by doing it, and that's all that matters. Okay, this is related to one of the questions, it's actually a quotation, "I don't see where this course is going." I'm kind of concerned about this because it's a big failure from my side if you don't see where this course is going. And I'll try to tell you where this course is going when we go to the next slide. Lots of things about the exam. Sample solutions, sample problems, more hints about the exam, and so on and so forth. The point is, I've already told you more than enough about the exam. Everything that is in the slides and nothing more will be on the exam. The self-studies, especially the coming self-studies, will not be relevant for the exam. All right? You will not be asked to sketch a Vensim model and draw lines and stuff like this. They're not directly relevant for the exam, but indirectly they are. Because if you get this feeling about feedback loops and their importance and all this kind of stuff, then you will be able to answer conceptual questions. Like, why is it important that a negative feedback loop has a goal or something like this? So indirectly, they are relevant for the exam as far as your understanding goes. And you can only get this understanding from doing stuff. Nothing more that is on the slides will be on the exam. There would be no questions, solve this, here is a problem, apply the problem-solving cycle to it, and write 2 pages of text. No. It would be, if you know the slides, if you understand every slide or every second slide, you will get a 6. It's as simple as that. And there can't be any sample solutions to anything. Do I have this point? No. It just can't be. We cannot have a sample solutions for the airport study or for the predator-prey model. Okay, last point. You don't want to receive Moodle emails. Well, nothing can be done about that. So you better create a filter or something and then put it in a directory. Yes? That's true. That is true. You can unsubscribe, but then I believe when I created the forum, I forced everyone to be subscribed because I want you to get all the emails. So if you unsubscribe, I will just subscribe you back. No, see, it's not to flood you with emails, but I think there have been so far interesting posts on the forum. And even if you don't care about them, that's fine. But there may be one person who does. So that's why I wanted everyone to be subscribed, and it's not a big toll, actually, on you. Okay, that's it. Where this course is going, again, I will try to reiterate, and probably I'll change this introduction in the coming lecture. We looked at finding solutions to problems. Oh, I have to speed up. First of all, what kind of problems we're dealing with. You already know. There is no sample solution. There is no formal algorithm how to solve these problems. We need human decision makers to find these solutions. Discussions, negotiations, stakeholder analysis, all this kind of stuff. Implementing solutions comes second. So these first 2 points just give you a flavor of what needs to be done before you even go to controlling these solutions. Right? So it's not that you start from Vensim. No, you start from the blackboard talking to your clients. What is systems dynamics about? Let me reiterate. The core goal of systems dynamics is to reveal interdependencies between system elements. And having done that, to highlight important feedback loops. That's all systems dynamics is about. How the elements are interdependent and what kind of feedback loops exist between these system elements. From a control perspective, it's simply, we consider the system as a white box as opposed to a black box. We put some input in and we want to understand how this input gets transformed to an output in the system, right? So contrary to a black box, we don't just take the system for granted like a weather forecast model. You just put some stuff and you get the probability, how do you call this? Probability density of the weather, I guess. No, we want to understand exactly what's going on, how this input is transformed to an output. I spent a great deal of time last lecture talking about modeling. We actually didn't have so much time to talk about the actual model from last lecture, which was the predator-prey model, but this was not important. The important thing was to understand what kind of models we're dealing with and what to expect from these models. What you should expect is not quantitative or real-life answers. You should expect just highlights of things that are important to you. Remember this picture with the X-ray and the ultrasound, right? You just get a highlight of a little bit of your system. So in that sense, every model is wrong, because you can always get a different highlight and claim that this is more important than what some other guy did. All right? We looked at the population dynamics model. It's a very important model. It's a prototypical model which can be applied to biology, economics, social systems, and it's, I think, one of the first systems dynamics models developed. We looked at the rabbits and foxes, how both populations fare in isolation, so the eigendynamics of both systems. So the rabbits explode or die, and the foxes just die if they don't have enough food. And then we coupled them together, and we saw the interesting oscillations. So coexistence of the two populations manifested through these kind of oscillations. This was what was also in the self-study. Now, this is basically, this lecture will be about going and building a model from scratch. We haven't done this yet. You had the model ready for you in the previous self-study, but here we build the model from scratch, and that's what you have to do in the self-study as well. How do we go about building a model from scratch? And this is basically, it tells you. First, you focus on the most important effects, the effects with the highest weight. Don't care about the little things, the little system elements or feedback loops that have some influence but insignificant. If you focus just on one dominant effect, that's already good enough. Remember, we take the system as a given, and we just have to model its elements, try to basically, based on your intuition, develop your system elements and their feedbacks. We do not care about the welfare of individual agents. We actually don't care about the welfare of any of the system elements individually. We only care about the welfare of the whole system, right? So in the population dynamics model, it happens that if the rabbits die, the rabbit population dies out, the whole system basically ceases to exist. So in that case, we would care. But there are other situations where we wouldn't be so concerned about how each system element is doing individually, but only collectively. What I mentioned with the discussions at self-studies, a lot about modeling is about intuition, heuristic approaches, so rules of thumb. How to identify feedback loops, how to identify system elements. This cannot be taught from a theoretical perspective. This is what you have to do, now do it. It's just really based on doing and learning through doing. And the same system, the same phenomenon can be described in different ways. Remember my example about cooperation from last lecture. We can explain it with people's sense of fairness, but we can also explain it with punishing people. So both of them would probably work. There is no formal way to model. So if you'd like to take this opportunity to learn how to do it, you really have to sit down and do it. You cannot rely on 15-minute or 45-minute of presentation about this. And we start from the simplest systems, and we build incrementally, right? We also talked about this last lecture. Start with something very simple. If it doesn't work, if it doesn't generate what we expect, build more and more. And actually, when you have your system, this is an important point. When you have your system, you can test that system, just as you can test a theory, right? You say, well, now if we apply this kind of input, we should get this kind of output. And if you don't, then your model is probably wrong, or it needs improvements. Just like in any theory, you come up with a theory, and then you come up with ways, with experiments to test it. If you can't test it, so if the theory is not falsifiable, it's not a good theory. It's the same thing with modeling. So let's start with the model without further ado. The model is about workforce and inventory, or production and inventory. And the situation is the following. You observe in your company, and people actually observe in companies, that there is a kind of a cycle between periods of low capacity utilization and high capacity utilization, and even not just high, but overload of capacities. Right? So what is the reason for this? Well, you might say the the demand is very volatile. So if the demand is very volatile, my sales will be very volatile, ergo my production will be very volatile. So that's the economic argument. It's basically caused by the market. However, if you look at data, basically, at empirical data, what you see is that sales or demand, they fluctuate a lot less than production. So there is something internally happening that causes this amplification of volatility from sales to production. And we want to understand what is this. What is that internal thing that causes the effect? We build a model starting from the simplest possible scenario. So let's see how to do it. First, the problem. What is actually the problem? Well, the problem is that production is less stable than sales or demand. And here I've shown you, I think I've also provided the source. Okay, no. You should have the source for these figures in the notes. What you see here is two industries. This is the oil industry, and this is some kind of machine tool industry. Well, let's look at this one. This is kind of the oil value chain, right? So you start from the drilling, you go through production of actually the refining this thing, and then this is basically the petroleum, the gas that goes into your car. So look at the drilling, and this is kind of growth rate, fractional growth rate over, yes, per year. The drilling fluctuates a lot, right? Then you go further the value chain, further down the value chain, so this is upstream. You know, this is very much upstream. You go down, you go to the oil and gas production. So it's basically that curve, this one, all right? It fluctuates slightly less, and eventually if you go to the demand, to the actual demand for in the gas stations, it doesn't fluctuate at all compared to this upstream. So that's one example why production along the value chain, so upstream, fluctuates a lot, production fluctuates a lot less than sales or demand. Another example is from this machine tool industry. Here we have the actual car sales. They fluctuate somehow, but if you go up the value chain, the ordering of tools for these cars, the demand for the production of these tools fluctuate a lot more. So basically we're going from upstream, downstream, and then finally we look at the GDP. And then it almost doesn't fluctuate. So that's a problem. It's an empirical fact. So something is going on. All right. Let's start. What do we want? An important thing is to, before even sitting down and developing a model, you need to define for yourself what you expect from that model. When you plot, let's say, production and sales, what do you expect? What do you expect them to look like? Otherwise, you cannot test your model, at least not in the at first glance. Well, we want to see something like this. Demand fluctuates a little bit, and production, well, it's a very ugly sketch, but you get the point. Demand fluctuates a little bit, and then production fluctuates a lot more. We want to get this from our model. Well, let's start building it. what dynamics is capable of producing such a behavior? So let's basically start thinking, okay, what kind of system elements do I need? Obviously, we have production on the one hand, and we have demand or sales on the other hand. So we identify two variables, production and sales. How are they connected? Through inventory. So we connect them through inventory. Now you see, you can already spot what are your stock variables and what are your flow variables. Remember, stock is something that accumulates value over time. Flow is something that is just like instantaneous flow, like energy and power, right? Power is just a flow of energy at any given time. And energy is actually accumulation of total consumption total consumption. So basically we connect them like this. Production goes to inventory, and then we take, this is our factory or our warehouse, we take stuff from here and we sell it at the market. Very simple. In a different, well, this is not really a differential equation, but if you want to put it in a mathematical form, it's simply like this. The inventory or the stock variable is simply the accumulation of what you cannot sell, basically, over time, right? You sum up over time. Simple as that. If you want to put it in a differential form, you just say the rate of change of that thing, so di dt, is basically the difference. So the rate of change at any given point of time of inventory is the instantaneous difference between production and sales at this point of time. But if you don't like math, just scratch that. You don't need it. See, we can have this nice diagram here. All right, but what else do we need? So this was basically connecting our two most important variables. But what does production depend on? Now you can think of, I'm sure you can think of many, many things what production depends on, but in the simplest case, we start with humans. Production needs people producing stuff, even though we have a lot of machines nowadays, but we still need workforce. So we introduce workforce here. And the workforce, mind you, we have not connected the workforce element, system element, to our system yet. It's just an isolation. The workforce depends, in turn, on a flow, and we call this flow net hiring rate. This aggregates all kinds of turnover that you have in your workforce. Layoffs, retirements, new hires, all this kind of turnover in workforce is captured here. So, in a differential form, your workforce changes according to a net hiring rate, which is constant at any given point of time, but of course in general it can be a function. It's not necessary that it's constant, let's say 2% over time, it could fluctuate. And this is basically a function how it fluctuates. All right, any questions so far? I think that's quite easy. The model is very simple. Yes. Oh, okay, I forgot to mention. Now, you can think that production depends in the long term, so let's say in 5 years or something, it depends on the amount you've invested in factories, in machines, the amount of capacity you've built up or outsourced or something. That's true, that's certainly true, and you can well develop a model which incorporates this. But in the short term, these kind of fluctuations that we observe, we want to explain them by short-term measures, in a sense. So we ignore the long-term effects, and we only concentrate on the short term. And in the short term, what production depends on is mostly people. So this is why we focus on the workforce here. Let's connect them now. We simply connect the workforce to production in the following way. We say, well, all these people that we've hired, they can produce stuff with a given efficiency or with a given productivity, right? So we say the production is linked to our people, to the workforce, in that way. So we simply have a productivity measure, which is a constant, and we multiply it by our workforce and we get a production, right? For example, if we have 200 people and each of them can produce 2 units per day, then we have our production for 1 day is 400 units. Simple assumption. It's probably a lot more complicated in real life, but we want to focus on the most important effects, not on the little details. Remember that. And we link them. So our production now depends on the workforce. There it is. But it also depends on the productivity of our workforce, this little e. See, that's how they're linked. And this is our model. Right? Is anything missing? Conceptually. I'm sure you can add more elements. We've already talked about this. You see, there is a negative feedback loop here. If your sales increase, your production has to increase, but your production would increase by increasing the workforce. Your workforce increases by increasing the net hiring rate. So in essence, you will be able to satisfy this demand, this huge sales demand, or this huge demand. So if, on the other hand, the sales decrease, your production will decrease by basically laying off some people. So the workforce is like a balancing feedback, right? It tries to, I'll get back to it, tries to get your production to the level that it has to be. You know, that your production doesn't explode or die down, but it tries to match your sales. So it's a negative feedback loop. But what's missing? Yes? Yes. So why is there no feedback between sales and the hiring, the workforce? Actually, there is a feedback. We just haven't sketched it. The assumption is that managers, they observe sales, or they observe the demand, and then they change the workforce accordingly. So there is an implicit feedback that we just haven't sketched. Yeah, of course, yeah. But something is missing. And we talked about this when I was introducing feedback loops. What is missing is the goal of the feedback loop. So that's an important guideline for you developing your models. Every negative feedback loop should have a goal. To what do we want to balance our system? And this is how we factor in the goal. Let me explain it now. We introduce target production. So to what we want to match our production, what is the target production? Well, that's basically the demand. Right? Our target production must be equal to the demand or to the sales. This is the goal of the feedback loop. And we call the target production PZ. I guess Z comes from Ziel or something. It's historically in the slides, but it's PZ. All right? And from here, you can derive the target quantities of all the other system elements. So, for example, the workforce will be simply the target production divided by the productivity of your workforce. So WZ. And now we can try to become a little bit more realistic. Of course, when you need to hire more people or to lay off some people, you cannot do this instantaneously. There are labor laws, work contracts, especially for Europe. I don't know how it works in North America, for example, but in Europe, you know pretty well that if you want to lay off people, that takes some time. If you want to hire people, interviews, maybe you hire the wrong people, you need to hire new people. So there is time, you need basically technical time, you need to adjust your workforce. And we call this the workforce adjustment rate, or the net hiring rate. And this is basically our tau. All right, tau is the adjustment time that is needed. So let me explain this equation to you. Now the net hiring rate, R, disregard the tau. Imagine we can hire people and we can lay off people instantaneously, or just kind of reproduce them from a machine. So we get what we need to hire is in fact our target workforce divided minus the workforce at this point of time. All right? But now, if we introduce this kind of adjustment time, we simply divide by tau. And for instance, if we want to hire 20 people, but our tau is 100, then we can only hire, well, 0.5 persons at this point of time, right? So we cannot hire all the 20 people now, but we can hire maybe one, and then one more, 2, 5, and so on. That's the idea of the adjustment time. So that should be all. This is the complete picture of the model. The only thing we've introduced, yes, it's also given here, but this is the complete one. Our sales or the demand determines our target production. Remember PZ. The target, so basically they should be equal. The target production determines our target workforce, WZ, which is basically PZ divided by E. Target workforce, together with the time to adjust to that target workforce, determines your net hiring rate at this point of time. That determines the increase or decrease in workforce, which determines your production, and so on. This is how the model looks like. And let's run it. You can build this in Vensim. I believe you have to for the self-study. And when you run it, we get that. We start, well, so let me explain this. We start reading this whole thing from here. Now, at that point of time, this is maybe 20 times 20, I believe. 20, yeah, about 20. Imagine there is a surge in demand or in sales. So very simple example. Your sales increase by 20 and they remain at this level forever. Right? So from 10 units, you suddenly need to sell 30 for basically eternity. So if your demand increases, let's go back here. Your demand increases, your target production, which needs to be equal to the demand, also increases by the same amount. And your target workforce would also increase. It's basically production divided by productivity. So your target workforce also increases. You suddenly want all these people to produce the additional units, and you want to keep them forever because your sales don't change anymore. However, you cannot hire all these people immediately, right? There is a adjustment time, and this is the net hiring rate. So your net hiring rate spikes, but then, so basically, out of, so let's say you were at equilibrium, you were not hiring anything because everything was matched completely. Now suddenly you need to hire a certain amount of people given by the difference between target workforce, current workforce divided by the adjustment time. And then there is some time, you can see this time, which needs to pass before you can hire all these people that you wanted, right? So at this point of time, you have already hired all the people that you wanted, and you stop hiring. So you have 0% hiring net rate. We'll continue after the break from this graph. So, and we're right on time. This is good. Okay. So we had a nice discussion about some of the survey feedback. And yeah, I'll try to incorporate actually, I'll try to incorporate this actually in the next lecture, starting from the next lecture. So I hope that's somehow an incentive for all of you to fill the second survey, because that really greatly helps better discourse in a sense. All right. So we looked at the results of our model. So let's continue with discussing the results. Remember, we needed to hire all these people, but we can't hire them immediately. It takes some time until we can hire them. And this is the point when we've actually hired all of them. This is how the workforce actually looks like, right? So it's not a pause, it's not a step, but we need some time until we hire all these people. Like we start from, what is that, maybe 90 people up to 150, and we need this time to hire them. This is due to the adjustment, to the adjustment time that we need. All right, so we've hired these people. It's basically the same graph. And the production simply has the same shape. Remember, production is workforce times productivity. So we simply multiply this graph by the productivity and we get our production. And I think in this example, the productivity is 1. Right? So they're basically the same. So what we see is our sales jumped by 20, I believe so. Yes, our sales jumped by 20. And our production adjusted with some time, of course. And this time is due to the delay in hiring. Is this what we expected to see? Is this what we expected to see? No, exactly. There is no, there are no fluctuations. Right? No variability in the workforce, and you have some volatility in sales, but you don't have more volatility in production. This is what we wanted to see. So obviously the model is incomplete. This is how it works. You start building a model, it's very simple, doesn't work, you introduce more stuff. And now one can think, here's where intuition comes into play again. One can think, well, what else do we need? We need qualifications for people. We need this and that. But we focus on the most important effects. And one of the most important effects is the inventory. We assumed that our inventory is simply like an instantaneous warehouse, which is just used to ship units from production to sales. It's like a tunnel, basically, right? Units from production go through this tunnel and then go to sales. But this is, of course, not how real inventories work. Most companies, I dare say not all, but a huge majority have so-called safety stocks or inventory coverage. This is, in a sense, the percentage of your sales that you want to have in your inventory. It resembles the reserve requirements for banks. All right, it's the same thing here. So there is a percentage of your sales that you want to be able to satisfy immediately without producing. And you store this in your inventory. And now the inventory is really like a warehouse and not just like a tunnel. So we need to incorporate safety stocks, right? And just as from the previous model, this is how your inventory would look like with a safety stock. Right, so you have some inventory, sorry, not with the safety stock, but this is from the previous example. If there is a spike in production, then your inventory decreases and it doesn't change anymore. But this is not what happens in real life. You have to go back to your safety stock level. So let's do this. Let's incorporate safety stock or inventory coverage. And it's pretty much the same way as before. We introduce target inventory, IZ, this one here. And the target inventory is simply, as I said, the percentage of the demand of the sales that we want covered. Hence the name, the inventory coverage. And Q, this parameter Q is inventory coverage. What's not clear? You had some questions? All right. Yeah. It's simple, right? So we have the inventory coverage Q, and this is what we want to be in our inventory at all times. But then again, and by the way, depending on the industry, of course, the Q is different, but let's say about 10% is a good kind of rule of thumb. But that's relevant. So, just as before, we need some time before we can bring our inventory to the desired level, right? So if we suddenly want 100 more units in the inventory, then of course we need to produce them first, and that takes time. Therefore, we introduce again another time delay, which is the correction time, or the inventory correction time, and we call this alpha. It's the same mathematical shape as before. This is what we want to have in our inventory, plus or minus, of course. Maybe we need to have 100 more units, maybe we need to have 100 less units. But it takes some time before we can get there. Therefore, what is our production now? We want to produce, obviously, enough to satisfy the demand or the sales, but we also want to produce something in addition to satisfy the inventory coverage ratio. So our target production now is the demand plus this is what we store in the inventory. Just in case there is a huge spike, we'll be able to satisfy it. And this is how the model looks like. This is our demand or sales. It determines the target inventory through the inventory coverage. It's basically this equation. The target inventory determines, so the inventory correction, which is K. So this is the amount of stuff that we add or remove from the inventory at any given point of time. K depends, of course, on the current inventory, the target inventory, and the correction time. Current inventory, target inventory, and correction time. This determines your target production, and everything else is the same way as before. Clear? I mean, it's basically the same model. We just introduced an additional negative feedback loop with a goal. The goal is this one to the model. So let's see how it works now. We put it in a computer or Vensim or some other software, and we have something better. We read it the same way as before. Our sales jump by some amount. Yeah, this amount. Let's say it's 50. And then it stays there. It's a very simple case. Maybe 50 more people were born, and then they want 1 unit each forever. What happens to our inventory correction now? Inventory correction, remember, is this additional amount of units that we want in our inventory at this point of time, right? So what will happen is our sales increase, our target inventory or our coverage would increase. Therefore, this is what we have right now. This is what we want to have, so that difference increases. So we need to put more stuff in our inventory because the sales increased. But we cannot put it immediately, right? We cannot put it at this point of time. Maybe we can put it over the course of 1 week due to this correction time. So what will happen is, depending on this alpha, and this is a case where alpha is very small. What happens when alpha is very small? Well, you overreact. This is modeling overreaction. So imagine this difference is 20. You had 10, now you want to have 30. Therefore, you need to have 20 more units. But you overreact. This is less than 1, 0.1 for instance. You overreact and you put 200. Right? So there's a huge spike here. Then in the next time period, you see, okay, I have 200, but I wanted to have 20. So I need to remove, let's say, 180. But again, you overreact a little bit. So again, you go like very, very, like from here, you spike down to here. So you overreact in both directions. When you need more, you put a lot more. When you need less, you take a lot less. And then it takes some time until eventually that difference is so small that your overreaction doesn't matter anymore. So there is damped oscillations here. You see, and they're still oscillating. A long time after your demand is stable, your inventory correction is still oscillating due to this overreaction. This overreaction causes your target production to exhibit these damped oscillations again, right? Remember, target production is, where is the target production? It's what you need to sell plus this inventory correction, right? So you basically add that thing, you add it to your sales, right? So you add this to that basically. You add up these two curves and you get this. So this is your target production. It fluctuates in the same way. Target workforce is given productivity 1 is the same as your target production. And then it takes you some time to hire this workforce, remember. It takes you this time to hire the workforce. And finally, the workforce looks like this. And the workforce is equal to the productivity, basically, given, production. The workforce equals production. Remember, they were linked with the productivity. Assuming productivity 1, even if you don't assume productivity 1, they will have the same shape. Just the scale would change. But the point is, there is a fluctuation here. So the model reproduces what we needed to see, right? There is a spike in demand, actually very well-behaved spike, I would say, and your workforce goes like that, or your production fluctuates like this. And what was the cause? Well, two things. It was caused by basically two delays. Delay in your inventory correction and delay in hiring workforce. Right? So of course, if you play with the delays, you can get other things, not just damped oscillations, but you can reproduce, let's say, perfect forecasting. Right? You don't overreact. Right? But you will play with this in the self-study. Okay. Yes, so this is basically what I just said. By introducing these two time constants, now we have two delays, and you'll see that delays are important. The model is, in essence, reproduces things successfully. In the self-study, you will have to play with these two parameters. See, these are good candidates for critical parameters, right? You can change them in the short term. Actually, they are short-term parameters. And you see different effects. And this is just an example. If you play a bit with the alpha, and the alpha was the adjustment of workforce, right? The time it takes you to adjust your workforce. No, was it? Let me see. Alpha was, oh yeah, it's the inventory correction time. So if you play a little bit with it, you see here we have huge overreaction, this one, right? You need some inventory, but you overreact, then you overreact again, then we have a little bit more overreaction if you change the parameter, and then here we have something more or less stable, right? Of course, if you assume that you can immediately adjust your inventory, you would have no oscillations at all. But since that's not what happens in real life, we have a good proof, a good case to claim that there is overreaction in real life. Yes?
So those three graphs are three different alphas?
Yes, yes. They are different alphas. And okay, this is the production, which is basically equal to the workforce. Remember, I mean, they're always equal, linked by the productivity. This is what the self-study is going to be about. And again, let me reiterate this. You can only learn and really understand how these feedback loops work by doing it. It cannot be taught. Even though you may understand it, you don't develop the intuition. So if you're interested, that's an opportunity for you to do it. Let's look now at the real case, however. This was just a Mickey Mouse example. Let's look at the real case, and this is indeed the real case done by McKinsey guys in a company which is called Fast Growing Electronics. It's obviously a fake name. There is a real company behind it though, but due to whatever confidentiality reasons, it has not been disclosed. The case is taken from the book of Sturman, Systems Dynamics, no, Business, or what was it? Yeah, the book, Business Dynamics, I think it was called. And it's a very interesting case because it happens a lot in real life. Let me explain it quickly. We have, all right, so we have this company is in the so-called high velocity industries. What does high velocity mean? Well, high velocity means that the demand and the prices are very dynamic. They change a lot. In most cases, prices go down, functionality is required to go up. Feature sizes go down, things become smaller with more functionality, more complex. Product life cycles become a lot shorter compared to the development times. And you can think of industries like that, electronic industry, computer components, laptops, transistors are packed more and more onto single chips. Product life cycles are in the range of 8 months. And the development time sometimes maybe even more than that. So imagine you have a very short time where you can make a lot of profits, or you have to make a lot of profits, huge margins, in order to make up for these huge development costs, which otherwise, you wouldn't be able to operate, right? You have like maybe 2 or 3 months to sell your product at the highest margin, and then it goes out of fashion. It happens with these things all the time. So these are the high velocity industries, and the most important processes in these industries are obviously product development. You have to shorten the product development cycle, and supply chains. Right? This is basically built from components all over the world. So supply chain becomes very important. All right, and this is our company. It's kind of used to be a new company. It experienced the following kind of effects: huge growth over 5 years, 50% growth per year. So by the way, this is per year over 5 years. So 50% per year growth in production, 40% growth in revenue. And now you can immediately see declining prices per year, right? You ship 50% more, but your revenue or your sales only increase by 40%. Why? Prices go down, that's why. And a huge increase in net income as well. And then this is a scenario where lots of startups can find themselves in. Fast growth cannot be supported by existing workforce, by existing processes, technology, and infrastructure. And then they have all these kind of problems. Long delivery times, lots of inventory buildup, low predictability of demand. What happens is that they give guarantees to their customers, meaning that the customers, or they give them the so-called price guarantees, meaning that the customer can cancel the order in the last moment. That's kind of a nice thing you can do to your customers. If you cancel the order in the last moment, you're not punished. So obviously when they do that, this results in low predictability in demand. And all this kind of stuff. Quarter volatility, that's something very important. Probably the MAS guys know a lot about it. It's basically, you have some targets that you need to fulfill in your quarter, and then at the end of the quarter, you haven't fulfilled a lot of them, so you have this kind of hockey stick phenomenon, where you try to fulfill your targets in units shipped or whatever, in 2 weeks, right? And then you start overworking people, pushing, trying to find shortcuts how to get these targets. The number, it's not mentioned here, but just think about it. The number of stock keeping units, SKUs, increased by a factor of 35. By a factor of 35 in all these 5 years. So the amount of products that basically they were selling, different products and services, increased times 35. It's a huge thing. And this was a problem for them. In fact, by this, you can't really pinpoint the problem, right? There is a problem, but what is it? We don't know exactly. This is where problem-solving cycle comes into play. You'll see it later. It's important to say also that different people, different managers had many different ideas about solutions. Depending on what they thought the problem was, there were so many propositions, like let's move to build-to-order production schedule, right? You only build stuff when you've secured the order, like expensive cars are nowadays. There were lots of different propositions, but the problem was there was no way to quantify or to evaluate them. Which one would be better than the other ones? You know, it's a similar problem, right? How to objectively quantify these different proposals. Even if we agree on some kind of proposals, how do you implement them? In what succession? What do you do first? What do you do second? There was even conflicts between some of the propositions. For instance, if you there was a proposition to reduce the lead time of products, so to get your materials faster from your suppliers. But then, of course, that conflicts with internal processes for evaluation of suppliers. It takes some time to evaluate suppliers. And then if you rush this, obviously these two things are conflicting. So the main problem was that there was not a problem defined, an objective problem. And based on what every individual thought the problem was, there were different solutions. It's a very similar situation for us. And what happened is some consultants from McKinsey came to help them out, and they developed a systems dynamic model for the whole situation. And they identified what causes all these kind of key problems and what are the main levers that you have to pull to address these problems. And we'll see this now. So these guys came, and for 2 weeks, they spent 2 weeks talking to people, to managers, to engineers, seminars, workshops. This is basically the problem-solving cycle, right? The first part of this course. You have to go and you have to talk to people. There is no algorithm for this. Yeah, so based on that, they found out the very important or very interesting and counterintuitive result. It seems that all this excess inventory that was building up was invariant to what the product was. In particular, even if you have a slow product meaning product which doesn't sell well, you've produced a lot of it, but now nobody wants to buy it. And it's natural that for these products you build up inventory, you build up huge inventory, you're unwilling to revise your estimates and to admit that this product is actually a flop and you have to discontinue it. So you can understand why inventory can build up for slow products. But what these guys found out was that inventory gets built up also for hot selling products. So very products in high demand. And that is counterintuitive. It shouldn't be the case. Actually, exactly the opposite is what you would expect. You cannot satisfy the demand, and you should have no inventory, basically. But this problem was invariant to the product. And this was a very interesting question now. How does this excess inventory emerge for hot products? And you can see now, there's a very easy trap that you can fall into right now. You can say, well, let's develop a model for slow products, and let's develop a model for hot products, slow-moving products, and hot products, and analyze them separately. See what is responsible for the inventory build-up for slow products and for hot products with the two different models. But that would be wrong, because if you tailor-made a model which is very specific to a given situation, then you can basically, the predictions or extrapolations that you can make from this model are very limited, because it's only built up for this particular specific situation. And you can always do this. You can always limit your problem scope and create a model which is basically useless. At the end of the day, what you want to do is to make predictions, right? To try, based on the mechanisms that you identify, you try to make larger predictions. Maybe policies, management practices, stuff like that. But you cannot do this if you develop two different models. What needs to work, or what needs to be done, is to develop a general model, and just by changing the parameters, it can apply to slow-moving products and also to hot products. So this is the way, and this is what the guys did. But before, obviously, you start building a model, remember we have to define what we expect to see, just as we saw with the oscillations in production. What we expect to see is the following. This is how the dynamics of a typical hot product looks like. So let me explain this figure. Let's start from here. This is time, and this is units produced. It's a hot product, remember. So iPhone 4S, for instance. You announce the product initially, and lots of people are very excited about it. They really want to have it now. So what happens is you get a lot of orders, even more than you can possibly handle. These are so-called, well, I'll talk about phantom orders in a second, but for now, you get a lot of orders in the very beginning, right? So your inventory, your backlog gets filled, your production currently is limited, and therefore your lead times basically start to increase. So basically the lead time is the difference between the time the order was received and the time the order can be actually fulfilled or shipped to the customer. So as you get more and more orders very fast, your lead times that you offer to your customers increase. The backlog, basically the backlog is, everybody knows what the backlog is? The backlog is basically the amount of orders that have already been accumulated in the manufacturer, right? And there is a delay between the order is made and it's actually received in a backlog. So it looks basically the same with a given delay, okay? But that's all right. So there is a some delay in your backlog, but they both increase because it's such a hot product and you simply don't have the capacity to manufacture a lot of it at the moment. And this is your inventory. Okay, so let's stop here. Oh, no, let's continue. So with time, you ramp up your capacity, you ramp up your production, and you're able to satisfy all these orders. So your lead times go back, your backlog goes down, but you end up with a lot of inventory. Right? This is what we want to reproduce for a hot product. Now let's look here on the upper part. This is our demand. Normally, that's how demand looks like. It's like a bell-shaped curve, or normally distributed, right? So initially, we have huge demand, and then this is the peak of the demand, and then it goes down. Remember, in the beginning, everybody wants to order a lot. Different retailers different wholesalers. They want to order the iPhone 4S for themselves, right? They know that probably Apple will have difficulties satisfying all the orders for different retailers, so they order a lot only for themselves, right? They order 100,000 units, and they hope that, I mean, it's perfectly rational if you think about it. If you order a lot, you may hope for special treatment from the company. You limit the amount of units that can be shipped to your competitors, right? Even though your inventory may increase, that's good because there will be such a high demand for this product that you will quickly get rid of this inventory. And most importantly, your competitors will suffer. They will not be able to sell the iPhone, and you will, right? So you get a lot of these initial orders. These are the orders, channel orders. Right here, and this is the build rate, so how fast you build your components, right? So you get a lot of orders, but it takes you some time until you build them, right? This is the time it takes you. This is the delay. This is the lagged response to the supply chain. So this is where you've satisfied, at this point of time, you've satisfied this amount of orders. But look what happens. At that point of time here, the demand peaks, and then it starts to go down. So just as you have produced a lot with a given delay, the demand goes down. All these orders that were initially made get canceled. That's why they're called phantom orders. And you end up with a lot of inventory. And the cause is the delay, this delay here. Or we assume that this is the cause, right? So imagine, I don't know how familiar you are with this kind of supply chain contracts, but when you make an order, of course, you can cancel it, given some kind of terms, of course. But if you order 100,000 units, you can cancel half of them and maybe pay some kind of punishment fee or whatever, but it may not be such a big deal for you. So all these orders, you think they're real, you produce them with a delay, but then they get canceled. And you end up, and the demand is actually low, gets lower, and you end up with a lot of inventory. This is what we want to reproduce. So the guys, the McKinsey guys, they developed this kind of systems dynamics model. Of course, it's it's a complex thing. We cannot show the whole model, but I'm going to show you the most important components of it. All right. Okay, so you have explanations for all these balancing feedbacks. Okay, let's start with here. Customers make purchases. So you introduce the product, and lots of people make purchases for it. So when you increase, let's say when the retailers or the wholesalers, they assume that there would be huge demand for this product. So these guys, they assume that there would be a lot of demand for this product. They would increase their channel orders. They would increase their orders, obviously. They would order more from you, from fast-growing electronics. As they order more from you, your backlog increases, obviously. So you get more and more orders to fulfill. It's like a queue, right? That you have to fulfill. The channel, your backlog increases. When your backlog increases, you cannot accept so many orders anymore. So you say, well, we're not going to accept 1 million units per month now. We can only accept 100,000 units per month, right? And then this kind of a balancing feedback loop until both of these get equal. But let's start from here. Initially, your backlog increases, or your queue of orders increases. What happens then, you're so full of things to do that you can't really promise concrete delivery times, right? You cannot promise, yes, you will have this product in 1 week. I'm still waiting for my laptop from Neptune, by the way. So, I mean, that's pretty much here. When the backlog increases, your delivery predictability goes down. When the delivery predictability goes down, the retailers, they want to have more of the product in store because they think, well, Apple cannot ship all these products. And we assume that Apple cannot ship these products reliably. They cannot promise me you will have 100,000 units next week. Therefore, I'd better be on the safe side and order more. Right? I want to have more in my shop, just in case. Right? So this is this kind of defensive ordering. So you order defensively, just in case something goes wrong. And this is a reinforcing feedback loop, right? So delivery predictability goes down. The retailers, they want to have more at their stores, which increases the orders and so on. And remember, we analyze the feedback loops given everything else is held constant. That's the important thing. So of course you can say, well, but I thought that this feedback loop was acting, so how can this thing increase from that feedback? Of course they act at the same time, but when we analyze them in isolation, so everything else held constant. So this is reinforcing feedback. Let's go to the left side. Your backlog increases, it's full of orders, and so you need to manufacture these orders. What you do, you order materials, you restage raw materials. So you buy more, let's say CPUs from Samsung, if you're Apple. But yeah, with these lawsuits, I don't know if they're going to buy from Samsung anymore. We'll see. But anyway, you have to order more materials, obviously. But of course, you can do this with a delay. You cannot get the raw materials immediately. Right? So there is a delay here. You have a huge backlog, there is a delay, you get these materials, but then there is an additional delay before you can build these new products. You got the materials, there is a delay before you can build them. After you build them, your inventory increases as well. Your inventory increases. If your inventory increases, then of course you can make more shipments. If you can make more shipments, then obviously, let's say your lead time would decrease. So you will be able to deliver your products faster. This is obviously not the case with my laptop, but yeah, we're here. As your lead time decreases, your customers are happy. They don't order defensively anymore. They're happy if they have less in their inventory. Actually, it will be profitable for them to have less in their inventory. Instead of ordering 100,000 units now, they will order 1,000 units per week as they need them, because they know they can get them in time. And then you have a nice balancing feedback loop. But, of course, and in this way you can analyze the rest of the loops. For instance, your backlog increases in the beginning. What happens? Your lead time increases, as I said. As your lead time increases, so I can promise you that you will get this product, but you will not get it in 1 week, you will get it in 2 weeks. As opposed to here, which basically means I can probably get it plus minus 3-4 weeks. Well, not minus obviously, but either in 3 or 4 weeks. Right? But here you can probably reliably say, no, you will get the product but 2 weeks later, because the lead times increase. This causes your customers to purchase ahead. Right? They think ahead. Okay, in 2 weeks I'm going to be needing 200 units more, so let's order them now. Okay, and that's a reinforcing feedback loop. And I think these are all the loops. Yeah. So this was the systems dynamics model here. And the guys run the model. And let's see what they got. Before we analyze the pictures, let me again remind you, the model formulation itself took 2 weeks. Right? So not just the interviews and the workshops and the different meetings with managers, but just formulating this model, it took 2 weeks. And most importantly, the guys didn't just say, okay, we had our interviews, now we go to our company and we'll come back to you in 2 weeks, we offer you a model. No, they stayed there and they interacted with all the managers, all the people involved in developing this model. They were asking them, okay, what do you think may be an important feedback that we've missed? An important process that we've missed? That just goes back to tell you about the feedback, the problem-solving cycle. It's very important. All right, and this is what they got. This is a slow-moving product, hot-moving product. Slow-moving product. The historical backlog looks like that. The model backlog looks like that. The inventory, historical inventory looks like this. The model inventory looks like this. This for a slow-moving product. Very good fit. Hot-moving product. The historical net inventory looks like that, right? This is in the beginning. You cannot satisfy all these orders, but you have a lot of them, right? And then just as you're able to satisfy them, they get canceled, the phantom orders, and you end up with a huge inventory. Model reproduces it quite good. So we have about 5 minutes, I think, so let's speed up a bit. What can we do from this now? Well, we can think about policy analysis. What can we suggest to this company now that we have the model? Is it just good that we reproduced some historical data, or can we do something more? And what you can do is you can basically do two things: standalone policy analysis, which means let's focus on this particular feedback loop and see what we can do with it, or you can offer this kind of integrated policies where you can do a lot of things together and you amplify all of these loops together. And we'll have a look. Okay, for example, you have an example. An isolated policy may be if you improve your forecast accuracy or product launch predictability, what will be the result? And you run it in the model, you see, well, we have average impact. However, if you reduce the delays in response to supply chain changes, so if you reduce these delays here, you have high impact. You know, this is already a good result. You would think that predictability in demand would be important, huge impact, but actually it turns out that it's average. Whereas decreasing your internal delays has more impact. And that's a good insight already. Let's look at integrated policy. We can do these things together. We can reduce our material lead time, so the time it takes us to get materials. We can reduce our planning cycle, and we can incorporate this build-to-order policy, for instance. And this is just an example. These are different policies. Shorter lead time, material lead time, shorter response time, and shorter order to receipt time. So this is basically the time between you receiving the order and being able to issue an invoice. And the point is, look at this. I mean, unfortunately, we don't have time to go through the details in all feedback loops, but you can understand them yourself, I'm pretty sure. Look at all this. They're only reinforcing feedback loops, positive feedback loops. The positive feedback loop, remember, reinforces positive things and negative things. It doesn't care, but you do. So if you put a positive thing into this system, it will get re-amplified and re-amplified, this positive thing. So if you do something positive here, or at the same time, all these different small effects would get amplified through these different feedback loops, positive feedback loops, and your result would be a huge, huge impact from this integrated policy. 1 more minute. So that is the example of self-reinforcing build-up. So this is just a positive feedback loop which can be influenced by you, right? So you know it exists. Let's put something positive in it. Let's order more materials before a product launch, right? And this will have a nice positive feedback. This is the last slide. Yes. Product life cycle, it's 2 slides. We can cover it next time. But this is the result from what we can do with the model. Now think about this. You start building a product and you encounter different bottlenecks. For example, you encounter material acquisition bottlenecks. You want to produce these iPhones, but you just can't get the materials fast enough. Well, you solve it. Then your throughput increases. Then you encounter a new bottleneck. You solve it. Your throughput increases. A new bottleneck. You solve it. Your throughput increases, and so on. Right? So this is attacking bottlenecks as they emerge. You can use the model for this. But what you can also do is you try to predict the bottlenecks from your model. This is using the model to anticipate the emergence of bottlenecks. And by doing this, of course, this is an ideal picture, but by doing this, your throughput, your process throughput, would behave much nicer, much smoother. Okay, so we're going to start next lecture with quickly showing you the last 2 slides from the project life cycle. It's very simple, but I hope you got the message today. Thank you. All right, good morning. There's a small technical difficulty. I wanted to change the slides in the last second, but it didn't work. So welcome to the, to the 6th lecture in our course. Before we start, as I promised, I would like to show you the results from the survey that we had. About 42 people out of 120 registered students voted, so that's less than, it's about 30%. It could have been somehow better, but I'll take these results as representative nevertheless. All right, so quickly, all in all, the feedback was somehow positive as far as my personality goes. I was trying to identify areas for improvement for the course and also for myself, and I think I found some. I'm going to show you those. But before that, the quick aggregated results. So the questions, most of you attended all the exercises. I appreciate that there were honest people who simply didn't care, and they were honest enough to say it. So most of you seem to be satisfied with the exercises so far. This could get a little bit better. I hope with the Vensim models it will get better. Well, I should have zoomed in so much actually. Yeah. Well. So I'm happy to see that somehow I managed to explain at least the most important things, and yeah, that's a good thing. Now, this is a question which I believe could be improved, and I was thinking about how to improve it. It's about how the exercises are coordinated with the lecture, and there is a good 10%, or let's say aggregate 25% of people who are somehow on the border between thinking that they fit and thinking that they don't fit. I will come back to this question when we go through the manual feedback. So this is my favorite question. Well, yeah, after the survey it became my favorite question. Yeah, so with my graphics driver and other PDF readers don't work for some reason. So let's discuss the manual input questions and the feedback that you gave me there. I tried to find out the main themes or the main kind of concerns that you have. The first one is this one. No formal way to solve problems is taught. Actually, it's a quotation. You see, this was not the purpose of the course, to teach formal ways to solve problems. The purpose of the course is to introduce the problem-solving part before we go to the systems dynamics part. Systems dynamics is basically about trying to find out how systems work and why they don't work. But you don't start from here, from that part. You start before the system is being built, by identifying the problem, trying to come up with the better solution, and then designing your system according to the better solution that you hopefully you have found. So the purpose of the first part of the lecture was just to give you a flavor that this thing exists, that you need to do problem solving. There was a general guideline in terms of the problem solving cycle, how you go about this situation analysis, selection of solutions, so on and so forth. But this course is not about formal ways for problem solving. In particular, given the fact that the problems we tackle, they don't have a formal way of solving them. It's all about you as problem solvers, individual problem solvers. You have to go through the discussions. You have to go through all these reiterations of the problem solving cycle, situation analysis, try to find out what your client wants. So it's actually difficult to teach a formal way to solve this kind of problems. How do you teach a formal way to solve the self-study with the airport? I cannot think of anything like this. So first of all, this course was about giving you, the first part of the lecture was about giving you an idea that problem solving needs to be done before you start modeling with Vensim or writing differential equations and stuff like this. So if you expected this, then probably I didn't communicate this well enough in the beginning. And second of all, there is no formal way for our problems. There are general guidelines or frameworks, but not a formal way. Second, some of you wanted more real-life examples of the problem-solving cycle. So more case studies like the airport. This is a good point. I'm thinking maybe we can drop one of the self-studies, in particular the fourth one with the SWOT, or maybe modify it in a way that there is a real business case behind it, where you can apply the SWOT and the problem-solving cycle. But that would not affect you, actually. That would affect the next batch of students. But it's a good point because, I mean, we had two self-studies for the problem-solving cycle. Either we can make them more precise, so reduce the scope of the problem, or we can make 3 self-studies for the problem-solving cycle. I have to discuss this with Professor Schweitzer and get his opinion, but it's certainly a point that I will keep in mind. Next one, there was a lot of suggestions, complaints about the self-study presentations. In particular, you wanted, or some of you, those who gave the feedbacks, wanted less presentations and more discussions. So if we have 2 or 3 groups presenting for 45 minutes, naturally this cuts down on the time we have for discussion. And there were suggestions, actually. I appreciate this. Not just criticism, but also suggestions how we can do this. Maybe just part of the problem is the problems are split among the groups. And I was thinking about this, actually, for a couple of days. And this is what I think now. You see, for the first part of the lecture with the problem-solving cycle and this kind of discussion-oriented self-studies, I think we had discussions. I mean, we certainly discussed the airport example. We tried to discuss the SWOT case. But importantly now, when we go to the Vensim models, and I will address this in the lecture as well, modeling is a lot about intuition. It's a lot about developing, doing it yourself, basically, learning by doing. There is no way that you can, or modeling can be taught in a way that you get a feeling how to identify the proper feedback loops, how to identify the critical parameters. There is no formal way for this. There is no theory for this. there is intuition. It's like learning to program some computer language, learning to program without ever doing it, just by somebody discussing no pointer exceptions or stuff like that. So the self-studies until the end of the lecture are going, well, let's say, what you can get from these self-studies depends a lot on you doing stuff, not so much on discussing. Because you can have 40-minute discussion on this feedback loop and this critical parameter, and you will think you've understood it. But when you get to do it yourself, you won't have this kind of feeling. I mean, thanks for that. I certainly do try, but this makes things actually more difficult for me. Because, you know, with great power comes great responsibility. So it's very easy from here to go deep into the ground. But I will try for this not to happen, of course. The airport cases, the majority thinks they were interesting. Still, there are people, 8% in total, who don't agree at all. And I was looking for some kind of manual comments to see why. I think I know why. So we'll get back to this as well. This is all right. The topics are interesting. I believe this could be improved. I did not write all the text in the self-studies, but now that I read it again and again, I believe there is something to be improved purely in the presentation style, so that's going to happen. This is also kind of a good feedback, but then again, these were just 4 lectures, so I'd be interested to see how this thing develops, this question in particular. I see value in attending the lecture. This is good. The self-studies should not be too difficult, should not take you too much time. And this is the most concerning question, actually, for me. This question was not present in previous years. I came up with it this time. And it seems that, I mean, I see this as kind of my fault, because there is a good percentage of people who don't see what the purpose of this course is and how each lecture builds on top of the previous one. I see this as basically failure to communicate this effectively from my side. Yeah, I mean, what can I say? My goal here is every time to reiterate the overall structure of the course and where we are currently. And I thought that would be enough to give you an impression of where we're going, where we're heading, but it seems not to be enough. So I'll be thinking how to maybe change the introduction of the lecture so that you get more kind of memories from previous lectures. The pace of the course seems to be all right. Okay, then I will not show you this. I mean, I will show you this, but kind of a stripped down version of it. So these were the multiple choice questions. Now we go back to to the lecture and to the manual feedback questions. I'm using a Acrobat reader because something is wrong with my what to do, because you've never done it. So the important thing for the coming self-studies is that you do stuff. And even though we may not have enough time to discuss every single feedback loop, every single parameter that you can vary, if you've done it yourself, that's good enough. Having said that, I'm pretty sure we're going to have time to address the most important things in all the models that we're going to see. What are the most critical parameters? What is the most important thing that you should get from this model? So this is my goal for the coming self-studies. But discussions, so bottom line is discussions will not help you for learning how to model. It's really learning by doing. And the purpose of the self-studies is to give you an opportunity to learn this, to develop this intuition. All we ask for is one presentation and one active discussion. We think that this is the minimum activity required, at least to get you interested and give you some kind of practical sense. So I don't see how more discussions will be useful for the coming self-studies. Another thing, groups were concerned that the value of their presentation is greatly diminished if they're not first, meaning that the other group would have probably mentioned everything that they wanted to mention. So they see this as a waste of their effort. It's wrong, because even if your presentation is identical, well, not identical, of course, but has the same messages as the previous groups, the important thing is that you did it and you learned by doing it. And this is the point of the exercise. The point of the exercise is not to polish up your presentation skills, but to learn how to do it. So this will not only help you, you've done it, but it will also help the audience, because if we reiterate a point, it's just more likely that the audience gets it. All right, so don't be concerned if your presentations have huge overlaps. And so far there haven't been huge overlaps, I have to say. But even if that's the case, that's not the important thing. You learn by doing it, and that's all that matters. Okay, this is related to one of the questions. It's actually a quotation. I don't see where this course is going. I'm kind of concerned about this, because it's a big failure from my side if you don't see where this course is going. And I'll try to tell you where this course is going when we go to the next slide. Lots of things about the exam. Sample solutions, sample problems, more hints about the exam.